Hi everyone. So welcome to tutorial 3. This is hands-on 3. There's a little typo here. So in this tutorial, you're gonna be able to run some code yourself. Um, as you've been seeing the whole morning, this is a typical workflow of Perturbo. So after you running Corner Espresso and when you're 90, you're gonna feed the wave function, the phonon perturbation potential from phonon, and the Unitarian U matrix to our interface program called qe2pert.x. This will read those results and write that into a HDF5 format files that we call EPR-H5, which stand for electron phonon in real space, or in linear gauge, if you will. So that's it. So first, make sure you have your Docker Perturbo installed in your computer to follow the workshop, to follow this tutorial. So I prepared the command right here for you. Make sure you change the path to your hand-on3 to the directory that you store your hand-on3 GitHub repo. So I'm going to initialize my Docker like this. This will take us to the directory called home user run. In this directory, you see your hand-on3 folder, and we can look inside. There will be two part of our tutorial today. Will be a polar material, gallium arsenide, and another one is an example where you actually incorporate the quadruple tensor computed in app init to use that to compute the quadruple correction to the electron phonon that we have been discussing in this morning. We're not going to detail into the theories in this section. Basically, we're just talking about these codes that you're going to use for Perturbo. So first, I want to make sure everyone are on the same page. Do we all have the Docker install completely in your computer? So, all right. So out in this tutorial, I will use the serial Perturbo, and I will with OpenMP implement. First I will set my number of threads I want to run in parallel by set OMP num thread equal 4. So in all of my subsequent calculations, I will run with 4 threads. So we'll start with the polar material gallium arsenide. So the first step, the starting point of our calculation is density functional theory, which will be in this folder right here. You can just copy the commands that I prepared in the GitHub and paste them to your terminal. Well, all right. So we just simply so these are very standard quantum espresso calculations. I will let us peek into the input a little bit. So there's nothing special here. We just specify the K point automatic K point at this step. We also in a Docker we should also have the pw.x executable. So if you are inside your Docker container, you should be able to execute this command without compile separate kernel espresso yourself. So scf.n. And also the T command here is just basically to print out the output to the screen just for demo purpose. So scf.out. So in this step, we are performing a self-consistent calculations to obtain the equilibrium charge density, which we will be going to use. We're going to be used for the phonon calculation. After finish the run, you can see there's an output and a temp file that we specify in the input. This file will contain the charge density. So what we want to do is just copy this to the phonon folder. Temp phonon. So if you follow, so now we are at step 2. We are ready to run density functional perturbation theory. The phonon input is still very standard. We're going to use the Q grid 2x2x2. Only one thing you need to make sure is that this phonon grid must be commensurate with the K grid you're going to use later. So here we're going to use 2x2x2 for phonon. Sorry. So phonon.x, specify the input. And bring out. So now we are running density functional perturbation theory with phonon.x executable from Kernel Espresso. So this calculation in my computer will take about 10 minutes or 15 minutes in with 4 threads. So just for saving some time, I would just, so in each folder, I prepare a reference folder where it will have the necessary output at each step for you to continue on the subsequent steps. So if you stuck at any step that I showing here, feel free to just copy those output into the current folder and just use that for the next step. So it will help you not getting stuck at any point, and you can feel free to ask me a question later if you have any problem while running this workflow. So to save time, here there will be 3 Q point in our irreducible Brillouin zone. It's just showing here, but so right here is the list of 3 point on our 2x2x2 grids. But I will just cancel this run right here to save us some time. What I'm going to do is copy the output from the reference. Here, reference temp. So in the reference temporary folder, you should you should see the phonon output where all the perturbation potential and dynamical matrix have been written out. In our workflow, we also prepare you a small shell script called phonon collect.sh. So this little tool will help us collect all the results we just computed, put it in the save a folder called save, and qe2pert is gonna go to this folder and read the necessary file to help us compute the electron phonon matrices. So there's a little note if that you are running a parallel version with MPI. The file extension can be changed from the VSCF to the VSCF1. So you can, so you might need to go to that file, the phonon collect file, to modify that part. So chmod, and then we execute it. So if successful, you see a save directory right here. And that's it for the phonon part. Does anyone have any questions so far? Okay, so now we have the phonon potential. The next part is to perform a non-self-consistent calculations with with our specified K-grid. So if you go to the NSCF folder and look into the NSCF in, you go down to the K point you see that these are the key point that you must manually provide it, which can be very simple with the utility in 1 year 90 directories. So um, so the script called qmesh.pl, the important point is that this grid has to be the same as the grid that you provided to 1 year 90, or the code will complain about incompatible grid. So we copy the electron density from SDF to here, and then we can run our NSCF calculation. This will take like a minute. So in the meantime, we can take a look at the next step, which is the 1-yearization with 1 year 90. So here, so in the 1 year 90 step, there's gonna be 3 commands you're gonna follow. But first, let us take a look at the win input. There's the 2 most important parameter that you need to turn on to true is write U matrix, where you specifically write the Unitarian transform matrix U and XYZ, and write XYZ equal set write XYZ to true. The last parts will be the very same K grid that you provided in the NSCF step. This grid can also be generated by qmesh.pl. And for tips to troubleshoot in the 1 year step, I would refer to David's talk in this morning. This usually very tedious step, but for this tutorial, all the parameters are adjust to optimize and relax a little bit. So so you can save some time when you run the 1-yearization step. Okay. So my NSCF calculation just finished. We should now have in temp folder the wave functions for running 1 year 90. So we change direct to it. So the first step is you must have the wave function inside the 1 year directory. You can either copy it, or to save some memory, you can just make a soft link to that to that output, NSCF output. And then run soft link right here. So we have it here. Okay. So there's 3 steps to run 1 year 90. The first processing step, PW to 1 year step to compute the overlap, and then we actually run 1 year 90 in the 3rd line. So first we run step by step here, and then PW to 1. So this step will compute the A matrix and the M matrix that the code will be using to minimize the 1 year spreading.
What exactly does the first line do?
It's just the pre-processing step where it's recognize some parameters for the actual 1-yearization step in step 3. So it's required for 1 year 90. Yeah. I think it's write out some files NNKP. I forgot what that files were, but that files needed for PW to 1 year 90. Okay. So we run 1 year 90. Okay, it's finished. You can look inside the output, W out. Okay. So if you finish your run, these are the files you should get. The most three important files are the center XYZ, the UMAT, and UDismat. We're gonna use these three files to run qe2pert with it. If you look at W out, your goal is to inspect the spreading of the linear functions and minimize it. For tips, again, David have gone through them in this morning, so I would suggest go to that talk. So, okay, so we have the wave functions, the potentials, and the Unitarian transformation matrix. We're ready to generate our EPR file, which should be here. So in qe2pert folder with two directory above, we have prepared a qe2pert.input. So as you look into these input, the parameter are pretty much self-explain themselves. You have a prefix, the out there where you specify the NSCF wave function, the phonon there where you specify the save folder that you generated in the phonon.x step, the grid you use, make sure nk1 times nk2 times nk3 equals to the number of k points that you specify in the NSCF step, the range of bands that you want to linearize, and number of linear function that you use. The L1 is by default is set to true, which means you're gonna rotate the electron phonon matrix to the linear gauge. So we just follow the step here that I prepare. Instead of copying the linear result, let's just shuffling them here. When then human and also link the NSCF result earlier. Okay. So you should have all of these ingredients before you run in qe2pert. qe2pert has been implemented with hybrid MPI and OpenMP, so you can run it as you want. Okay. So if you run it in parallel with MPI run, you need to specify the number of pool for the K points that you're going to use equal to the number of MPI tasks, or the code will complain about it. So for example, when you run 4 MPI tasks, you need to specify the endpoints equal to 4. So right now the code will are computing the electron phonon matrix and then rotate it into the linear gauge for interpolation later. So does anyone have any question up to this step? Okay. Okay. So when this finished, you will have a YAML file output, which will contain the necessary information about your qe2pert run. So these are all the related parameters that you use for your qe2pert. And also in the temp folder, you see prefix elph.85 file. So this is the electron phonon matrix on the core script. The point of this file is saying if you detect that your linearization is not too good, you can go back to the linear step, redo the linearization, and then you can add to the qe2pert input the parameter called load if load if load EPH mat to true. So this parameter will signal the code will go to the temp directory to read the ELPH file, and then the new one-year results to redo the rotation of the electron phonon matrices. So that's it. That is the end of the qe2pert step. You should see the prefix underscore EPR H5 here. So in any other, so this is the start of any subsequent perturbo calculations such as interpolation, transport, or electron hole dynamics, etc. So you are pretty much all set for all those up until this step. So for the next step, we will demo some just one calculations using this file. More details will be shown in all the tutorials later tomorrow.
Question here in qe2pert input file. So we have DFT band minimum and band maximum, right?
Yes.
So do we plot the band structure and see which window we want to take here, or is there a inbuilt function to see that? The value of Q band minimum and Q band maximum, how do we choose that?
Oh, those are the band that you correspond to the band range you specify in one-year step. So if you go back to WinFi, it will be the number of band that you specify here. Yeah. You need to take into account the band that you excluded from the NSCF2. Suppose you run NSCF for 100 band, then you must specify the excluded from 25 to 100 here. And so this the DFT min max will still go 1 to 24 up to that. Yeah. So we should already have EPR. Now let's perform a example with Perturbo using this EPR file. So in this tutorial, I will run EPH mat, which is interpolation of the electron phonon matrix, and plot the electron phonon coupling strength on top of the phonon bands. So let's go to Perturbo-code EPH mat folder. So in this folder, I already prepare the input for us, which you can either generate it using Perturbo-py, or just go to our website to learn more about all of the relevant parameters here. So let's just go quickly through each of the parameters. So prefix is the name of the system. We specify the cal mode to EPH mat. FK list and FQ list are the list of phonon of electron and phonon momentum that you want to interpolate. So band min and band max here are corresponding to the band that gonna be summed over in the GNM, if you remember that. So we will only sum over the band number 5 here. We can take a look at the K point. Cast then K point, and also Q point. So in this file, the first line will specify the number of points that you want to interpolate. The first 3 columns are the coordinate of the momentum. And then the 4th column will specify the number of points between these 2 points that you want to interpolate. And with that, we can just run Perturbo that you already have in your Docker image. Specify per input. Oh, I'm sorry. Yeah, the very first step is to have the EPR file in this folder. So I'm just gonna soft link it from the qe2pert directory. Right here. And then we rerun it. Okay. So this signal, the interpolation is really fast. And after this, we should have the ASC file, which is the legacy file here. You can take a quick peek into it if you want. Okay, it's too tedious. But the main output that we're going to use to post-process with Perturbo-Pi is EPHMAT YAML file right here. We also prepare a simple Python script that using Perturbo-Pi to post-processing it. So in your current Docker, you can import the Perturbo-Pi post-processor. This is the command to read the electron phonon matrix from the YAML file, and then you can update the parameters to plot using these commands. For more information, I would go to the Perturbo-Pi website to learn how to set all the output, all the plotting parameters. But for now, we can just run this Python post-processing script. So Python 3, plot EPHMAT. Okay. So running this will give you this file right here. So gas EPHMAT.png. I have some trouble for open the file from Docker. So I have to go back to my actual terminal. Turbo. If you open that file, you should get what I included in the GitHub page. Okay, so that's usually how you run Perturbo. So you go from QE to 1EA, feed it to qe2pert, and then obtain the EPR file, and then run Perturbo.x with that EPR. So a quick note about polar material.
Sorry, before you continue, Kara, there's a couple questions.
Okay.
One of them is, well, actually, they're kind of related. So the questions are, how do you generate the gallium arsenide _band.qpt and .kpt files?
How do we know the points for interpolation?
Yeah, so how do you generate those files?
Oh, so for that file, so the Q grid are specified in crystal coordinate. So usually I use the tool which called, let's see, qe2pert. I think this is quite handful. This is quite handful tools that you can use to generate the K grid. Yeah, so for example, I can this tool will parse out kind of special input and actually generate the high symmetry point. So I can demonstrate it very quick here. Let's see if I have it. Say V1 from a thread. Let's see. So if you have an SAF input that we provided earlier in PW step, I think you can use this tool to generate the K grid. And we can see here that all of the high symmetry points are provided here. So I hope that answers your question. Is there another question?
Yes. The follow-up question is, any high symmetry path will be enough?
Yeah, it's up to you to specify the high symmetry path. You can usually I refer to the literature, like to see what path people usually see and plot on top of that.
Thanks.
Okay. Okay, so as we know from this morning talk, the electron phonon matrix actually have two parts, a short range part and the long range part, which is very important in polar materials. So we in Perturbo, we by default, if you don't specify anything, the code will compute both parts and interpolate in your grid. But for the short range part, usually you don't need a dense sampling near the gamma point. So it's sometimes better to separate the two parts from each others. So the only difference will be in the EM sigma part, which will be explained more detail in the subsequent tutorials. But in this step, you compute the imaginary part of the electron phonon self-energy. So if you go to one of the folder, sigma electron polar, and look into the PERT input. So the relevant, so you can, in this step, you can compute, so if you don't specify the polar split parameters, if you just leave it empty, the code will automatically compute both parts using the grid you provided here. But if you specify to polar, then only the long range part will be computed. Or if you specify to RM polar, the code will only compute the short range part, which sometimes is faster in some case. So that's the only mention that I want to note on these polar materials. So did everyone get the electron phonon plot at this point? It's quite simple. So the next part of this tutorial is how you would incorporate the quadruple correction into the electron phonon matrix. So the electron phonon matrix can be described using a multiple expansions. So you have the dipole, quadrupole, and then octupole. Depending on the materials, then some of these will be important. So, and specifically for a piezoelectric material, the quadrupole correction is very important, and we will show in the result of this tutorial, by the end of this tutorial. So to have the quadruple corrections, we just add one more step to our workflow. So which is so in Perturbo we don't have the routines to compute the quadruple tensor, but we will use the app init code to do the linear response calculation to get it. So if you look at here is the full formula that we use for the quadruple corrections. For more detail about the theories for quadrupole and how we apply this correction to real material like silicone, lead titanate, or gallium nitride, I will refer to these three papers right here. So the quadrupole enter the equation in this part. You see Q here, so it's Q kappa alpha beta gamma. It's a rank 3 tensor. After you perform the calculation with app init, you should have the file named tlw3.abo. In this tutorial, we'll just provide you the output, and I'll show you how we use the tool to parse out the necessary information from this file for qe2pert to read. So let's navigate to the second part. Okay, so it's in silicon with quadrupole. We're gonna do that in the qtensor folder right here. Sorry. So in this folder, we'll have the tlw_3.abo, and our utility is in this folder qtensor util. There will be two versions to do this. So initially we have a code that use H5 Fortran to parse, which require you to compile H5 Fortran library on top of the HDF5 library. But here I have a newer version called qtensor HDF5, which only require the wrapper compiler h5fc from HDF file library. This will automatically compile if you specify enable Fortran when you make your HDF file library. So in our Docker, it will be in opt HDF file bin. As you see, there we want to use this wrapper for compilation. So if you are already in Docker, you can just copy this command to compile the Fortran script. So when you finish, you will see an executable qe2pert right here. Go up a folder and you run that newly created executable qe2pert like this. So the code will prompt you to provide the output file name from AppInit. So in this case, we just type that here, .abo. So if everything running correctly, you will have this message where it tells you the number of atoms in your system. You have 2 atoms in your unit cell for silicon, some information about the quadruple tensor, and if you do a quick ls, you should have the qe2pert.h5 file right here. The next step is to copy this file to where you're gonna run qe2pert and add the prefix to the name of the file. So I'm gonna copy qe2pert to qe2pert, adding the prefix xi, qe2pert.h5 to okay. Okay. Okay, sick. Okay. This is a previous run. Forgot to delete the output. Okay. So after you let me remove this. Okay. Okay, so after you copy the qe2pert from the previous folder in your in qe2pert file, you should have this ingredient. The other part are similar to what we did so far for gallium arsenide. So for the rest of this tutorial, you will do exactly the same thing for gallium arsenide in the PW PH1 folder. So there's nothing new at this step. So I would recommend you to run these calculations yourself to obtain the EPR with the quadruple correction. So first we run SCF, okay, X. Okay, so from this step, feel free to ask me a question and finish the tutorial. I'm just gonna run the whole thing to obtain the EPR, and I'll make sure you follow through by the end of this tutorial. So step input. Okay. Copy to phonon. Let's get to phonon. We will repeat the phonon step. So again, this should take like 10 or 15 minutes. So you can copy the save directory from the reference to move on to the next step, if you will. Okay. So does everything work for you so far? Right. Is there any problem showing up? Okay. So I'm gonna just copy it here. So here I suppose that I only run phonon and have the save folder ready. I'm gonna run nscf. Okay, it's done. Go to running. Tones, tone. So that's not. It's run up. Okay. So we are ready to run qe2pert with quadruple. Okay. So okay, so we have all the ingredients to run qe2pert. The input for qe2pert will be exactly the same from the previous step. The code will automatically inquire for the Q tensor file and incorporate the correction to your adjoint phonon matrix. So we run qe2pert. Let's run that in. Okay. Which is reading them here. Okay. So what I did was I forgot to run when you it's gonna be 90, and then okay. Let's see. Um, okay. Okay. Should be done. Okay. Okay, I just rerun the 90 step, and now we see there's SIU mat, udismas, and then center XYZ in this folder. Earlier, I forgot to run 90, so that's why the code complained, because the file actually didn't exist. So should be ready to run qe2pert again. Okay. Perturbo-code. Okay. Right. So if everything is running correct for you, you will find one small message right here saying that find quadruple tensor, quadruple correction activated. It's a little typo there. Okay, and that's it. You now obtain the SI EPR H55. You can perform the very same calculation with this as we demonstrated in the previous step. I'm not gonna, so for the time being, I'm not gonna show all the calculations, but you are welcome to do so. So this is from our paper right here to compare the electron phonon with dipole correction only and with dipole and quadrupole corrections. So as you see here at the zone center, especially for the acoustic phonon mode, without quadrupole corrections, the electron phonon coupling is really deviated from the DFPT. So the DFPT actually can capture the long range and short range part, but it will be very computational, expensive to do so for sufficient dense grid for transport calculations. That's why we need this to capture correct electron phonon coupling in our interpolation workflow for transport calculations later. This will be the end of my tutorial. I'm welcome to take any question that you have from the audience and from the remote participants.